Okay, so we are in the last chapter of the last meeting of the third chapter. There is I wouldn't say terribly bad, but less, not like a piece of candy, less pleasant news that we will have one more homework, and it will be due not next, not like in a week from now, Monday, but earlier. So for the course, it would be ideal if it will be also due Monday, but I understand that it's too short notice and you may be already busy for the weekend. So Wednesday is the latest. So I will announce a new homework. I was showing its assignment at the beginning of previous meetings. And on Monday, we will start new chapter. Then Wednesday, I will show the key for the homework that you'll get today. And then we'll continue through the next chapter. And in 2 weeks, we'll have another presentations, which will be based on the lab next week. And it will be most important code that will be used for the rest of the class and will be used as the primary tool for the research project. Okay. So here is this homework that, well, some of you already have submitted homework 5. This one is 6. So homework 5 is agreed Monday, 6 on Wednesday. And sorry for a little short notice. This one is not easy. Some of you have already done question 2 of part A, which was extra credit for like number 3. And I intentionally wasn't including it in the key for homework 3. So it's the thing here is just taking matrix elements, the concept that you already went through, and I will refresh it today. The thing in number 3 is very similar to our homework 4, but now I suggest we try to do it by pen and paper rather than with MATLAB. If you can do it with MATLAB, you can make an auxiliary thing and build a partial credit, but for us, for the progression forward in the course, it would be really great if you try to do it by pen and paper, and it will be the major credit from the whole this one is, it may sound scary as it is formulated, but it is quite easy. If you are or were taking differential equations, basically it's one of the simplest differential equations that everyone solves with guarantee. This one, we already covered it in the class. So if you look through the Heisenberg equation of motion, you will see solutions. And it also deals with like ball falling with a free acceleration gravity. So it is a solution from high school physics, but just in everything we did before we add angular brackets, and basically it is the same. And this one also not the easiest, but not the hardest. So if you took differential equations, it will be 5 minutes. If you took only calculus, it will be 20 minutes, let's say. But overall homework, please plan on investing at least 2 hours. So it is maybe, it's not the hardest intellectually, but it is one of the most solid homeworks in the whole class. So it's like not a kindergarten simplification. It's true adequate for 3rd year of the college. So just not too hard, but please plan on doing it. Okay. So I'm going to mumble something before we go to details. Where is my staging point? Right here. So we are going into three directions, where we are browsing in a space of ideas and models. One direction is different theories, another direction is different models, and the image that I was just showing seconds ago is oversimplification. We already went to many systems, at least in the aspect of quantization. So we did one-dimensional, three-dimensional, and two-dimensional boxes, which correspond to like quantum dots, nanowires, nanocarbon nanotubes, like realistic nanosystems. So we are already placed our foot into the door for real life. Before we go to the next chapter, I want to introduce I hope it will be not a rotation, but it will be another little effort on getting through. I cannot say it is a new theory, but it is very practical, new aspect, new view on the time-independent Schrödinger equation. And the things, the title of the section that we'll go over will be Schrödinger equation in matrix formulation. So if I need, or any of us needs to summarize the whole course in 5 or 10 minutes presentation for broad public, this equation will never come to the front. So it is not the most glorious or something important to the general public, but from practical point of view, it is like setting up a second engine to your airplane to give more flexibility in solving real life problems. So if I want to formulate it as a bridge, it's not a bridge between equations and real life. It's mostly like a bridge that tries to establish friendship between Schrödinger and Heisenberg. So Heisenberg expressed everything in terms of matrix elements, expectation values for observables, and maybe you remember, maybe not, but it speeds up all calculations and allows us to focus only on one thing or maybe a couple of things that we are observing and forget this multidimensional wave function, which is a big plus mathematically. Schrödinger's main achievement that his equation in vast majority of situations is linear, which is a big deal for from a mathematical point of view. So there are no ambiguities. There are multiple solutions, but they do not conflict to each other. The worst thing for differential equation is nonlinearity. When with the same or similar initial conditions, you have divergence of answers. So they want to answer the same thing, but Heisenberg is focusing on one or two observables of things, and Schrödinger is just predicting more philosophically wave function of everything, or object that we are focusing on. Can we match together and find golden middle so that we will be solving linear mathematical equation, but focusing on much smaller number of objects? So finding maybe wave function only in specific point of space, or finding wave function projected on one of the basis states. So we are going to travel from continuous space, where wave function is defined in Schrödinger approach, to discrete space, which is much closer to Heisenberg. Make sense? Okay. And I will show only the camera, but if any of you really want the shared screen or If you don't like to look at me, I can do it. This view is used just so that I better point and discuss in more human-oriented way. So here is the equation that we need to go over. Later on in class, we will use it, and equation on the top and on the bottom is the same. If you are happy with it, if you understand what it is, and there are no questions, right now I feel comfortable to say just stand up and leave the class or disconnect. So there will be nothing except background for this equation and verbalization what it is. So this is matrix equation on one hand. On another hand, it looks very much like time-dependent Schrödinger equation. Specifically, we do have an object that replaces wave function here. This column vector, you can say it is wave function psi. Here it is the same object psi, and here is the matrix that does replace Hamiltonian operator. So we have time derivative of wave function equals minus constants I over h bar, then operator of total energy, and then wave function. And the goal of this equation is predict how wave function evolves forward in time. The difference is that typically we have wave function defined as position and time, and dependence on position is typically continuously distributed. So you can walk in the Cartesian space forwards and backwards with infinitesimal steps. Here, there will be just a couple of elements of representing wave function. And in some cases, it can be 3 or 4, but it's discrete number. So we are converting Schrödinger equation into discrete form. And instead of differential operator, which in some sense it's also matrix, but on the dimension is infinity squared. If number of independent points for wave function is infinity, then number of independent points in the matrix corresponding to total energy operator is infinity squared. Here we go to let's say dimension of the wave function 2 and dimension of Hamiltonian 2 squared. So if you can do it, would be really great. And just looking forwards, because you can also flip through the slides. This is possible. This is doable, and we will get practical benefits from this approach in the rest of the course. And maybe some of us will get benefits even from this approach even outside. Whew. No, I do not want to read this ugly writing. Okay, this stuff is not as bad. I remember once upon a time in this class, we were practicing Taylor expansion and Fourier transform. And it was all done intentionally. So what is the main idea, if you want to summarize it and get away from transmitting radio signals and speaking more about mathematical philosophy? So Fourier transform serves to represent continuous function with a discrete set of expansion coefficients, right? So, and here I summarize it. So it works both in mathematics and for quantum theory. So a wave function can be represented as a summation of basis functions, each of which comes into the superposition with discrete coefficients. If we know for sure that in the problem that we are solving, wave function never takes any other state rather than phi1 and phi2, then instead of describing wave functions as a continuous thing, we can always tell it is either this or this with expansion coefficients. And we will need to only monitor and write equations for these expansion coefficients. Make sense? So this is a second chance to stand up and do it. It's the only new idea. So the equation on the previous two slides back was summary. It's expected outcome of the whole meeting, and this is the main idea. So instead of writing equation for the whole function, we are going to write an equation for expansion discrete. Very few expansion coefficients. Sometimes it can be more than 2, but few. I used these notes in the past, but so it's the same idea. Instead of a function, it's just a set of discrete numbers. And in homework number 4, we were solving what would happen to particle in the box if it is prepared in the superposition of ground state and first excited. Which means we were speaking, later on we introduced density methods, but initially when we were discussing it, it means that it will be always either in state 1 or state 2, and one can speak on the language of representing what happens to this electron in one-dimensional box, only with 2 numbers at each point of time, expansion coefficient over state 1, expansion coefficient over state 2, and we did select them as 1 over square root 2, 1 over square root 2. In the homework, maybe these numbers will be changed to something else, but the idea is here. So another philosophical idea rather than mathematical. You may remember myself and the whiteboard with 3-dimensional axis showing our browsing in the space of ideas. So one axis is different theories, another axis is different models, and third axis is perturbation, which is would bring us as closest to the realistic life, because in all characterization experiments, one is probing the system with something, typically with electromagnetic radiation. Same like well, basically the whole chemistry can be chopped on 2 segments: synthesis and characterization. So synthesis, when a kid places Lego elements on the top of each other, and characterization when he or she tries to kick it and see how strong it is. So the idea of representing wave function as expansion coefficients is mostly important and mostly fruitful when the system is being under probe, when someone is probing the system, when someone is trying to promote it from ground to excited or do something similar. Today, we are not doing it, but we are formulating a basis. But if you're thinking very, very critically, if you are thinking, if you look through notes, scroll back what you have heard today, which I doubt, but sometimes it happens, one may develop a critical statement like all solutions that can be obtained from this discrete representation can be obtained by other methods that we covered before. So it will not be glorious win over all other methods. But it is a basis for the possible future when one needs to take into account perturbation from external world. And to be a little provocative, there is a big lie of quantum theory, and I'm just formulating it in a provocative way. If one is reading only one book through the life, I mean in academic life, only one textbook in physical chemistry or quantum theory, one can arrive to a deception that if system is excited to ground state, it will stay there forever. According to postulates of quantum theory, it is so. But in real life, it's never so. And it is where pure quantum theory fails, where one needs to include external perturbation, where one needs to say that typically systems are not isolated. So if one wants to go into real life and describe the systems which are not isolated, then the basis, the approach that we are going to cover today is most fruitful and beneficial. So you will not see much of blooming and tasty fruits today, but it is a solid background for possible future considerations. It's just a little disclaimer. Okay. Those are little notes that I think we all are aware of. If we are in the continuous wave function representation, then a good wave function must obey normalization. The function star multiplied by a certain integrated must give star. If one converts this property of normalization from the basis of continuous wave functions to the basis of discrete set of expansion coefficients, then this convolution of continuous function corresponds to product of row and column of the expansion coefficients, which will be scalar product, which should also give 1. And it is the stuff that we were covering when speaking about MATLAB dyadic products. So ket is either continuous wave function or column. Bra is either continuous wave function conjugated or row. And when one is speaking about bra and ket, it means I do not want to be specific. I can mean either continuous or discrete, but it describes the same physical object. I disagree with myself. It's not a new idea. It's just basic math. But if one is introducing the operator in between bra and ket wave function, then the result of this convolution, instead of 1, will give us expectation value of the observer corresponding to this operator. And here is, I think it is ugly writing, not only because of my laziness, but also because it is not in new material. It is what we did before. So if we are practicing this expectation value stuff in terms of expansion coefficients, then our bra is C1, C2 with wave functions. Ket is C1 star, C2 star with bra functions. And then if one opens brackets, then the expectation value can be expressed as product of expansion coefficients times the object which appears as a convolution of the operator of an observable and basis function bra and basis functions ket on left and right. If you have only 2 basis functions, then in this expression, total number of these so-called matrix elements will be 4, because there are like two elements in first bracket, 2 in the second. When we algebraically open, there will be 4 terms like this. So Partially, we covered it with MATLAB and with density metrics for homework number 4. And the words that would be very appropriate to say here, that expansion coefficients may change due to time evolution or due to external perturbation, but matrix elements are found in stone once and forever. So if our box doesn't change its shape and size, then we can say that whatever we do with it, quantum state of a box will be superposition of its eigenstates. And if at one day we need to find an observable, and one day will be by Wednesday, one can find matrix elements of operator of interest, for example, position, between different eigenstates once and forever. And one can do it first, and then do the time dependence in this expansion coefficients next. And you do remember, time dependence comes just from phase accumulation, right? Okay. And one doesn't need to focus too much on things that I'm telling right now, because they are not new yet. I'm just reciting things that we were going over several times, maybe from a slightly different angle. So this is a little better calligraphy, but the same thing we already discussed. So first line is definition, how we find result of measurement expected in average expectation value of measurement. Next line is how this equation is converting if our wave function is expressed in a discrete basis. And last line is the first term that we discussed in details on previous slide, and then the rest of the terms. So if the system is in the wave function psi, which can be represented as superposition of first and second basis states with expansion coefficients C1, C2, then expectation value of operator A can be composed as a summation of products, or in the product there is a time evolution term and then matrix element. In substantial number of textbooks, this definition is swallowed, skipped, and not focused on. But I'm just trying to bring it up with a little more details, because it is a thing that I missed when I was taking the same course in my undergraduate studies. And when at the end of the course there were problems and exams, I just was missing concepts. So try to bring a little more detail. So this is not so much scientific, chemical, or physical concept. It's more mathematical consequence of this main definition in the discrete basis. Why are they called matrix elements? It's not the most successful terminology, but since we do have two independent counts of the expansion coefficients, one with star and another without star, 1, 1, 1, 2, 2, 1, 2, 2, and then this count is presented in the matrix element 1, 1, 1, 2, 2, 1, 2, 2. So basically, this A something is object with two indices. Object with two indices is comfortable to represent as a matrix. And it is something elementary. Therefore, we call it matrix element. Whew. So here is absolutely the same thing. Definition of matrix element in a matrix form. if, and the top line here is also could be useful from mathematical way if we ever need to practice this approach. So if we express our wave function in terms of expansion coefficients, if at the same time we express our operators, not only operators of observable, but all operators in terms of matrix elements, then standard procedures such as operator acting on the wave function and scalar product, and specifically such as finding expectation value of an operator is expressed as rho by operator by clone, or both rho operator and clone are expressed in a discrete way. So this one corresponds to psi, this is to A, this is to psi bra and ket. And it is the same as writing psi star A psi dx. So if we are happy, if this terminology and notation doesn't induce too much irritation, we can slowly go into our main goal for today, to the Schrödinger equation in a discrete form, which will be expressed in a similar terminology. So we also need to express Hamiltonian operator in the form of matrix elements. This is a boring note. Just skip it. Close your ears. I'll tell it for myself. If products of expansion coefficients are stored in form of density matrix, then finding an expectation value can be expressed by a so-called trace operator. Trace of a matrix is a summation of diagonal elements, and if one multiplies the density matrix by an operator and then takes trace, the result will be the same as by practicing discrete wave function approach. So trace is the same as finding expectation value. So slowly approaching to the main thing that we need to do, and I will soon tell new things. I'm watching time, know that we have about 10-12 minutes, but it's plenty of time to finish out. So, what is our goal? Well, I'm removing trivial goals like finish and leave as soon as possible, but if we are inside this context and we want to achieve the discrete Schrödinger equation, what is the practical barrier in going from continuous to discrete wave function? I may formulate this practical barrier as presence of the continuous wave function in the Schrödinger equation. And we already formulated that we do want to remove it. We want to get rid of the wave function in the rigor and on one hand. On another hand, we want to keep all benefits of the wave function. So to have some traces of it that would keep everything that we need from it. So the way to remove wave function from an equation, we want to have a prompt, is to multiply it by another wave function and integrate, right? So if we multiply the whole equation that contains wave functions, each term we will multiply by another wave function and integrate, one would practice orthogonality property, and everywhere where we have a pair of wave functions, we'll get either 0 or 1. if it was basis functions. And if it was not basis, some real time dependent things, it will be projection on a basis function. So once again, I remember myself in a similar class. Of course, I was not as dedicated as you guys. I was coming to maybe each second or each third meeting, therefore missed a lot. But it was like keeping 5% of the material is most the realistic thing. So I think that one can take home. If one wants to get rid of the wave function, one may practice orthogonalization, normalization principle, multiply by another wave function and integrate. So it is what we do have here on the board. So if there are two wave functions, this result will give either 0 or 1. So from now on, if you were taking time easy, now it's about for the last like 9 minutes of the class, it's time to focus. So first, Schrödinger equation in Ryan-Head notation. The wave function is represented in form of expansion coefficients. Now I'm going to plug 2 into 1. And then multiply. Then I need, so if I plug 2 into 1, so it is time dependence, time derivative of the wave function, which is summation of the first and second wave function with first and second expansion coefficient. And on the right is Hamiltonian operator in this wave function. Does basis function depend on time? No, because we found it once and forever. It comes from time independent Schrödinger, and it doesn't have time. So when we practice time derivative, it will apply only to expansion coefficient, where with basis function can be believed with high confidence as time independent. So one can swap places, wave function and then the expansion coefficient. Then, after doing this thing, we are multiplying left and right by wave function bra m, or m can be either 1 or 2, can be wave function 1 or 2. So I'm just carefully plugging in, and it will be m time derivative c1 1, m time derivative c2 2, constant m h1 c1 m h2. Reading out loud equations, I think the worstest thing that instructor can do, it shouldn't do. And the expansion coefficients are not operators, so we can swap order once again. This one goes here, this one goes here. And then we will have time dependence of expansion coefficient and matrix element, not matrix element, convolution of eigenstate m and eigenstate 1, which will be either 0 or 1 depending on what we choose as m. Then the same story for second term, and for the last term, it will be matrix elements of energy operator and expansion coefficients. So basically, it's already the answer that I'm looking for, but it looks ugly and maybe it doesn't look comfortable for analysis. So what I would like to do is to plug literally values of m equals 1 and equals 2. So if m equals 1, then the convolution of 1 and 1 will be 1, convolution of 1 and 2 will be 0 because of normalization. If m equals 2, convolution of 2 and 1 will be 0, convolution of 2 and 2 will be 1. Then I'm plugging it into our equation. So I will write two lines. First, what would come out if m equals 1? Second, what will come out if m equals 2? So because of this property, here we drop the second part. And because of this property in m equals 2, we drop the first part because of normalization. And here, as we were wishing, we did remove wave function on the left part. It's only time dependence of the expansion coefficient. Here it's time dependence of expansion coefficient 1. Here is time dependence of expansion coefficient 2. On the right, we do have matrix element of the total energy operator between wave functions 1 and 1. Matrix elements of the total energy between 1 and 2. So this one is, again, our equation that we are looking for. I'm just going to rewrite it once again. So these two equations for two elements can be summarized in a matrix form, right? If we look here in the first line, it includes superposition on the first line, right side. It includes 1 and 2. Second line, it includes also 1 and 2. So it could be expressed as some matrix multiplying the column vector of C1 and C2. And if we scroll back through our mind about row by column multiplication, it looks very much like multiplication of the matrix of the Hamiltonian onto the expansion coefficients column. So I'm going to bring this equation. And if you need me to make additional steps between previous and this slide, I can do it. But I hope it is kind of self-evident. But if not, I can answer now or after the class or in the mode of emails. So if we open this equation, it will be equivalent to stuff on previous slide. Okay? So it's just matrix equations is just a collection of linear equations summarized in form of matrix. For C1, that is composed of C1 and C2, and for C2, that is composed of C1 and C2. It's just a more compact form. And the matrix that determines time evolution of these expansion coefficients are matrix elements of Hamiltonian. If you accept typical matrix notation, it will be this equation that you were looking for. So the little discouragement only here, only today, only in this class, that if we do not have external perturbation from outside world, then typically this H12 and H21 are zeros, and then the evolution will be trivial. But as soon as we have a laser chemist trying to pump or probe molecule with external perturbation, these elements, non-diagonal elements of Hamiltonian will pop up, and this will be the only way to describe quantum properties of a molecule under external perturbation. I'm looking, yeah. Here we have only first and second, and those are zeros. But it is only here in the class. In the big life, it is a little more advanced. So thank you for your patience. Meeting is done. You're welcome to depart or disconnect. I'll stay here and answer questions if any. Homework 5 is due Monday, homework 6 due on Wednesday. And feel free to send me any emails. I'll be happy to address. Okay. in spite of homeworks, I hope you have a nice weekend and you will not develop irritation against the class because we have to do this. Kennedy, do you have questions? If no, you're welcome to disconnect. And I'm going to end.
Thank you.
Thank you.